Question number 71. How many time constants will elapse before the charge on a capacitor falls to 0.1% of its maximum value in a discharging RC circuit? So here, charge is given by Q0 e to the power minus t upon RC. So let's write t equal to n times RC. So Q equal to Q0 e to the power minus n. Here, value of Q is given as 0.1% of Q0 e to the power minus n. Q0 will cancel out. So e power minus n equal to 1 upon 1000 or e power n equal to 1000 or n equal to log 1000 base e, and that will be equal to 6.9. Now, question number 72. How many time constants will elapse before the energy stored in the capacitor reaches half of its equilibrium value in a charging RC circuit? So, Q equal to Q0 1 minus e to the power minus t upon RC. This is for charging RC circuit. So, Q equal to Q0 1 minus e to the power. In place of t, we write nRC, so minus n will be left. Now, energy stored is equal to Q square upon 2C. So, Q square 1 upon 2, it will be equal to Q0 square 1 minus e to the power minus n whole square divided by C. So this value is half of equilibrium value. So 1 by 2 of Q0 square divided by divided by C times half must be equal to this value 1 by 2 Q0 square upon C times 1 minus e to the power minus n square. So 1 upon 2 equals 1 minus e to the power minus n whole square. So this will give 1 minus e to the power minus n equal to 1 upon 2, which implies e power minus n equal to root 2. So this will become 1 minus 1 upon root 2, so root 2 minus 1 upon root 2 e power minus n equal to 0.414 divided by 1.414 or e power n equal to 1.414 divided by 0.414, which is equal to 3.414. Now we take log. So n equal to log base e of 3.414. So this will be equal to around 1.23. Question number 73. How many time constants will elapse before the power delivered by the battery drops to half of its maximum value in RC circuit? So P equal to EI, and the maximum value of P will be equal to E times I0, because E will remain constant, only I will attain its peak value. And for charging circuit, current is given by I equal to I0 e power minus t upon RC. So power delivered EI equal to EI0 e to the power minus t upon RC. Here it is given that this power is half of this value, maximum power. So 1 by 2 EI0 is equal to EI0 e to the power minus t upon RC, from where we get e to the power minus t upon rc equal to 1 by 2, and the t equal to be right n times rc. So e to the power minus n equal to 1 by 2, or e power n equal to 2, we take log. So n equal to log 2 is e, and that will be equal to 0.69. Now, consider question number 74. A capacitor of capacitance C is connected to a battery of EMF epsilon at t equal to 0 through a resistance R. Find the maximum rate at which the energy is stored in the capacitor. When does the rate has this maximum value? So here, Q equal to Q0 1 minus e to the power minus t upon RC. This is case of charging capacitance. Energy stored. Energy is given by 1 by 2 Q square divided by C. That is 1 upon 2C times Q0 square 1 minus e to the power minus t upon RC whole square. Now, rate of energy stored, R equal to rate of energy stored in capacitor equal to dE upon, if we write U in place of energy, that will be better. So let's write here du upon dt. So du upon dt will be differentiation of this. So Q0 square upon 2C, and this will be twice of 1 minus e to the power minus t upon RC into differentiation of this term will give, this will become 0, this will give e to the power negative sign minus t upon RC, and differentiation of this minus t upon RC is minus 1 upon RC. So we have got R equal to, here this is Q0, Q equal to CV, or we can write C square E0. So E0 is E square divided by, here 2 will cancel out, this minus sign will become plus. So C square E square divided by, here there is already C, and from here there is RC, and then inside with 1 minus e to the power minus t upon RC multiplied by e to the power minus t upon RC. So this will be epsilon square divided by R times, if we multiply e to the power minus t RC inside, so e to the power minus t upon RC minus e to the power minus 2t upon RC. So we have got the relation for R. So this is the relation for R. So e square upon R and e to the power minus t upon RC minus e to the power minus 2t upon RC. Suppose this is equation number 1. Now, we have to find out its rate of maximization. So suppose we differentiate it dr upon dt. So differentiation of this e square upon this capital R. So e square upon capital R, and differentiation of this will give minus 1 upon RC times e to the power minus t upon RC, and this will become 2 upon RC times e to the power minus 2t upon RC. For maximum value, dr upon dt must be equal to 0. So if we equate it to 0, so what do we get? We will get RC will cancel out. So we will get e to the power minus t upon RC is equal to twice of e to the power minus 2t upon RC, or one term e to the power minus t upon RC will cancel out. So 1 equal to twice of e to the power minus t upon 2 t upon rc, or 1 upon 2 equal to e to the power minus t upon rc, or e to the power t upon rc equal to 2. So if we take log, so we will get t upon rc equal to log 2 base e. Now let's further evaluate it. So we have got the value of t as t equal to rc log 2 base e. Now at this value, we have to find out this r. So maximum value of r we can say. So r equal to e square upon capital R, e to the power e power t upon rc is 2. So here we have e to the power 1. So this will become 1 by 2 minus. This will become 1 by 4 because it is double of that, e to the power minus t upon rc equal to 1 by 2. So e to the power minus 2 t upon rc will be 1 by 4. So we put this value here 1 by 4. We simplify. So e square upon 4, this will become 4 minus 2 upon 8, that is 1 by 4. So e square upon 4r, and that is our answer. We have got time as rc log 2 base e, and the rate of change, maximum value, is e square upon 4r. Thank you for watching.